So for the last talk of this morning, we have Chunyin, and he's going to talk about the topology of preferential attachment.
Hello, everyone. I'm Chunyin. Thank you very much for staying for the last day. And special thanks to the organizers, particularly Tamal and Tao, for making this conference possible and allowing me to speak at this conference. So today I'm going to talk about the topology of preferential attachment. So this is another random topology talk. In the program, I said this would be about theory and computation. And by that, I mean I'll spend most of the time talking about the theory and I'll address the computational issues at the end. Okay. Before I start my talk, some self-advertisement. I'm finding a postdoc for next year. So if you're hiring, please don't hesitate to let me know. Okay. So preferential attachment is a random graph process that produces graphs that look like this. Okay. What is this? This is a snapshot of the internet back in the early 2000s. Each node is a web page and each edge is a hyperlink. So as you can see, there is a dense core of nodes at the center. And as a topologist, you try to contract it. That's your natural instinct. But as a graph, this topologically speaking is just a bulk of the circle. So it's not that topologically interesting. So we want to come up with some more interesting topological description of this object. The other question is that we want to separate the intrinsic structure from the results of random fluctuations. If I write a Wikipedia page of myself today afternoon, the internet will change by a little bit, not by too much. That will probably not affect the intrinsic structure, but you want to be able to tell the difference between the two. And both of these point towards the study of random topology, which I think by now you've been very familiar. Okay. So I'll say a few words about random topology in case you're not convinced that this is interesting yet. And then I'll describe the preferential attachment model in greater detail. And finally, I'll share with you my recent result on preferential attachment. Okay. So far, any questions? And can people hear me in the room and on Zoom?
You may not see the feedback on Zoom, but
okay.
Okay.
Yes, it's
good. Okay, so if there's any question, feel free to stop me at any point. Okay. So random topology. In TDA, we start with the data set very often, and then we build simplicial complexes and look at we look at persistence diagrams, and we say that okay, points far away from the diagonal are important, and they're the signals we care about. Implicit in this pipeline is the philosophy that size is the only thing that matters. We care about large cycles, and these are the signals we care about. But this is not always the case. Here we see two squares. You should not need a PhD to see it. But if you do a PhD and learn topological data analysis, and then you look at the persistence diagram, you're very likely to conclude that there's only one loop, which is not desirable. And the obvious issue here is that the small square is too small for the persistence diagram to pick up. So as a probabilist, one message that I'm trying to push is that instead of looking at size, we should think of surprises. Okay. By which I mean, we can see two squares not because whether they're big or small, but because random points do not behave in this way. So if you spread salt on the table, it's highly unlikely that it will form squares. It's highly unlikely that they will fall on the edges of a square and they refuse to fill in the center. That's why we see squares. And so, in short, signal is what is not random. But if you subscribe to this philosophy, the signal is not not random, then you have to ask what is random. Okay. So we have seen two talks about random topology, so we do know quite a bit about random topology, and I'll give you a very brief survey of what the classical results we have. And this will be a sample of the results, so don't be upset if you do not see your name here. We know quite a lot about Erdős-Renyi clique complexes. We know the expected Betti numbers. These are works due to McHale and Meckes. And if you want to look at finer topological invariants, Costa et al. Have a paper about the fundamental group, telling you when it's free, when it's not free, when it's hyperbolic. And you can also go to higher homotopy groups and see when it's a homotopy sphere. And that is the work of Mellon in very recent, it's 2023. We can also say a lot about random geometric complexes, which arise very often in TDA applications. Again, we know quite a lot. McHale, Meckes, Jorgenschauer, and Adler have some results about the Betti numbers, both the expectation and the limiting distributions. We know quite a lot about the persistence diagram and persistence as well. Omer mentioned some results, also some results due to Hiraoka. And if you want to look at joint distribution of the Betti numbers, Thomas, Owada, and Wei have some papers about these as well. So we do know quite a lot about random topology. So why do we want to consider yet another model? One reason is that many models that I've just mentioned are homogeneous models. Okay? So every point is exactly the same, every edge is exactly the same. But if you look at something like this, it is highly unlikely to be homogeneous. Okay, my Wikipedia page is very likely going to be very different from tomorrow's Wikipedia's page. So the internet is not homogeneous. Many real-world data are not homogeneous, and so we want to study these data with a lot of heterogeneity. And the preferential attachment model is precisely such a model. It was proposed by Albert and Barabasi back in 1999. The idea is to construct a random model that can explain the so-called scale freeness of these networks. But in order to describe the model more clearly, I will content myself with a much simpler picture where I draw people as nodes. Okay. So the model goes like this. Okay. We start with a small graph, and then we add people to the graph. And the people are more likely to talk to already popular people. Okay. The way to formalize this is to say that the probability of attachment is proportional to the degree of the nodes. We will add the tuning parameter delta so that we have more flexibility in our model. So we have one family parameter for the model. And then we add the person to the graph, we update the graph, we update the degree distribution, and we move on to the next step. By which I mean we add more people. So since every person wants to talk with the already popular people, the popular people will become ever more popular, and this is known as the rich get richer effect. So this is the setup of the model. We start with a small graph, we add people to the node, they're more likely to be friends with all the already popular people. Any questions so far? Okay. No. I'll share with you something that we already know about the graph. We know how to count triangles in these things, which is nice because that will be the simplest simplex beyond nodes and vertices. We can write down the asymptotics of expected number of triangles. For our model, it is number of nodes raised to a sublinear power. If you tweak the details a little bit, you will get different asymptotics, but we can write them down. If you go to the network science literature, you may have seen the term clustering coefficients. That's roughly the proportion of triangles in out of all possible triangles. And since we can count triangles, we know quite a lot about the clustering coefficients as well. And there's nothing that stops you at looking at triangles. We can actually count arbitrary subgraphs. So tetrahedra, squares, pentagons. If you give me a small subgraph, I can give you the asymptotics of the expected number of such subgraphs. So by I mean these people who wrote the paper about this, and I'll apply the results. We know a lot more, but these are the results that are more relevant to our application. So, but we're topologists, we're not happy with this graph. So what we'll do is that we will consider the clique complex of the graph. That will give us a simplicial complex, and then we'll compute whatever topological invariants we can define. Okay, so that brings me to my result on the topology of preferential attachment. This is joint work with my supervisor, Professor Asymptotics, my co-supervisor, Professor Yu, and my undergraduate mentee, will be her. Our theoretical result concerns the expected Betti number. This is the simplest topological invariant, the simplest moment. We also can say something about the homotopy groups, but that will not be the main point of today's talk. So before I show you the analytical results, let's look at a simulation. So every curve here is a random instant of the preferential attachment graph. They all have the same parameters, they're just different random seeds. The x-axis is number of nodes. As you add people to the node, the topology changes, the Betti number changes. The y-axis is the second Betti number. So each curve you keep track of the second Betti number, and you do this 500 times to get 500 curves. Okay. There are a number of interesting observations here to be made. First, the increases. This is actually pretty surprising because usually in many random simplicial complexes, you see that the Betti numbers increases and peaks and falls down. The intuition being, if you do not have sufficient connections, the holes cannot form. And if you have too much connections, the holes get filled up by the higher order simplices. It does not show up here. And the intuition is that the higher order simplices appear in a rate that is much slower than the lower order simplices. So as lower order holes are formed, they're killed at a rate that is too slow that it doesn't decrease.
So, sorry.
Yes.
In this plot, you don't have the radius. So you are doing the Reeves complex filtration or what?
So I have a graph and I just look at a clique complex. So there's no parameter, no radius. So all you can think of it as the radius one. Yes. The number of nodes. Yeah. So you keep adding people to the graph, or keep adding nodes, which I think of as people. The second thank you for the questions. Please do stop me at any point. The second observations we can make is that the growth appears to be concave, which is not too surprising given that the number of triangles is they also grow concavely. So you need those triangles to form those holes. You need those to fill up those holes. The third observation is that there is this curve. I cannot point here, so I'll point here. There's this curve, which is way up higher than the rest and is an outlier. It is not too surprising that we have an outlier here because the preferential attachment mechanism is known to produce these outliers. In the internet, you have like giant pages like Wikipedia and Google. So here we have a graph that happens to have a very large Betti number, and it is not too surprising, even though we do not have a like closed form analytical description of the distribution. Okay, so here is our theoretical results. Okay, we proved that the expected second Betti number is basically the number of nodes raised to a sublinear power up to some constant. And the power depends on the preferential attachment strength. The stronger the preferential attachment strength is, the larger the power is. And since the exponent is 1 minus 4x, it begs the question of what happens when the exponent is negative. And you can show that the expected Betti number is bounded. It doesn't converge to 0, it's just bounded. Finally, there's nothing special about the dimension 2. If you replace all instances of 4 by 2 times dimension, you get exactly the same result, and that will be the higher dimensional analog. Now, if you need more time to stare at the statement, I have copied it on the whiteboard. And the people on Zoom, you can use a print screen magic to so that you can look at the statement for however long you want. Yes.
And what about Q is equal to 1?
That's a good question. Q equals 1 is a special case. The expected Betti number is just linear. And the proof is entirely different for this statement. It's actually much easier. So for dimension 1, dimension 1 is a critical dimension, is a dominating dimension. You have more edges than the number of vertices and the number of triangles. So a simple Morse theoretic argument will show you that the expected Betti number is just I should write down something. It's just n minus 1. N minus 1 times number of nodes. Plus small O of number of nodes. Is this still visible? It is visible, yes. M is the number of new connections you make every single time. And this is pretty straightforward Morse theoretic argument. You just look at because the number of higher order simplices are dominated. This proof is much more complicated. Any other questions about the statement before I move on? If no, this quantitative statement has a qualitative interpretation. So as I've just mentioned, the Betti number at dimension 1 is going to be unbounded in expectation because it's linear. Now, but if you increase the preferential attachment strength, you see more and more complicated topological phenomena. And at a critical threshold, the second Betti number will start to become unbounded in expectation. The argument simply being 1 minus 4x will start to become positive. And so we get concave growth. And if you further increase the preferential attachment strength, the third Betti number becomes unbounded in expectation, and so on and so forth. So if you increase the preferential attachment strength, more and more complicated topological phenomena can arise.
Sorry.
Yes.
Increasing the preferential attachment means that I'm attaching to more and more popular, or the opposite.
I'm more and more likely to attach to the popular people.
Yeah. Okay.
Yes.
Okay.
Yes. Yes. I did not write anything down to make that precise, but
No. It's just wanted the intuition.
okay. So I've claimed the theorem. I should give you at least a sketch of the proof. The main idea is that the growth of the Betti numbers is driven by these spheres, where you have a square equator and 2 poles. And if you count the number of spheres, you get something close to being correct. It's not quite correct because these spheres can be stacked on top of each other. So if you have another pole that's connected to the equator, you get a new dome. That will increase the Betti number by 1, and you can do this arbitrarily many times. So if you count spheres, you'll be counting. You'll be choosing and choose 2 domes, and that will be quadratic in the number of domes. But the Betti number is just linear in the number of domes. So what you should be counting is not sphere, but domes. There are a number of subtleties to make its argument precise. First of all, Betti numbers is not count, so you need some homological argument to make that precise. The second issue is that you need to identify the square dome as the dominant driving force, as opposed to say pentagon or hexagonal dome. But squares are important because square is the smallest thing that can give you positive Betti number. And in many random simplicial complexes, the smaller things arise much more frequently than other objects, and hence they dominate the growth of Betti numbers. There are a number of minimal cycle results in the literature, but unfortunately they're not phrased in terms of homological algebra, so we need to do that. If you just want a statement about homology, you can get away. You can just work on the chain level and get everything you want. But unfortunately, my argument depends on some relative homology argument, and I do not want to work with relative cycles. And so we need to translate that into homology. And finally, we need to apply the graph counting results to get the actual asymptotics. We have a formula for every single graph, but now we're dealing with family of graphs like squares, pentagons, and so forth. So you need to be systematic about your arguments so that you don't have to do everything like one by one. So if you believe I can handle all these subtleties, then you have to prove that the expected Betti number is roughly the number of nodes raised to some power. So this is a computational conference, so I will try to show you some computational results. Yes.
What was your preferential attachment in this graph, what you were showing? What was the value of X?
The value of X is, I've forgotten the value of X, but I can tell you what 1 minus 4X is. 1 minus 4X, if I'm not mistaken, should be 2/9. So, yeah. And I think that's all you need to know.
Yeah.
I think it's 5/7 or 2/7, something like that. Yeah, but anyway, this is all you need to know. We have seen the simulation, so we can take average and take log, and hopefully the 1 minus 4x will show up as the slope of this plot. So if you do the operation I just mentioned, you get this plot. So the black curve is the Betti number, is the average Betti number. The dotted curves are the estimates we have for our proof. You can see that the upper bound is pretty good, at least on the log scale, and the lower bound is very bad because it's bad even on log scale, but it works because it has a correct order of magnitude. And it kind of looks like that they are pretty flat at the end, but that is an illusion. If you plot 1 minus 4x, the lines with slope being 1 minus 4x, you get the green dotted lines, and the slope does not seem to have stabilized. So we are still in the finite regime. We cannot get the convergence yet. This does not contradict with our theoretical result because our constants are like 10 to the 18th and 10 to the minus 30 something. So this covers the entire plot we see here. But yeah, we're stuck with the finite regime. Okay. So I'll say a few words about the computations. We use Scripser, which, as I understand, is probably the best I can do in terms of quick complexes. Our computation for Betti numbers stop at 10 to the 4th nodes. After that, we have memory issues. Our estimates concern the Betti numbers of smaller subcomplexes, and we sum them up. So we can go further for the estimates. We went up to 10 to the 5th, but beyond that, we didn't try even harder. I think we don't have memory issues, but it takes longer and longer. Another issue I want to mention is that we have to compute the average. We need to look at a large number of graphs. So we use 500 graphs here, and it is important because we've seen that there are these outliers. So estimating the mean is not easy when you have outliers. So we have a large computation, and we have to repeat that for many times. So this is so if anyone has interesting ideas of how to do that, please let me know. And it is also typical of statistical applications because you very often have to like resample your object, and then you have to rebuild the persistence diagram, so recompute the Betti numbers. So I'd like to comment that in a lot of statistical applications, you do need big computations and repeat them many times. Okay, what lies ahead? So this result is simple results because we look at the simplest topological invariant, compute the simplest moment, and we have a very coarse estimate. So there are many ways we can go from here. We can say something about the homotopy connectedness of the infinite complex. We do not have tight results yet, but we can say something. If you're interested, we can talk more. If you're statistically minded, you may also want to refine the estimate. So that was a pretty crude estimate. So it would be nice if we can say something about whether the constants, whether the expected number converges, expected Betti number converges when you normalize it. Can we say something about the limiting distribution? So that would be an interesting direction. Another interesting direction would be to consider a random simplicial model, so we can add simplicities as we go, as opposed to just forcing the topology at the end. This is more as an art than science because it's difficult to come with a nice model that's convincing and yet also manageable. And finally, it would be interesting to look at other non-homogeneous complexes. So this is one non-homogeneous complex. There are many other complexes like the subclassic plot model, and I don't think people have looked into the topology yet. So that will be a story for another day. Today, I hope I've convinced you that random topology is cool. And in particular, preferential attachment graphs have interesting topology, and there are a lot more interesting questions out there. If you want to know the details of the argument, the archive paper is on the slide. And if you have not got sick of listening to me, this on the right, we have a video of my previous project about finding small holes in data sets. But if you've already got sick of listening to me, I will stop here. Thank you very much for your time.
Thank you for the very nice talk. Any question? Yeah, okay. We have one.
Yeah.
And you want to click on that, so you're like putting triangle,
That's a very good question. There are a number of sub questions here. First, what does the clique complex mean, and what does the Betti number mean, and what we're trying to do with our lives. So the clique complex is okay. I'll try to tell you something to convince you that it's not too bad a model. In many real-world networks, when people start to make friends with each other, they'll fill up the triangles. They know, for example, if like we collaborate, they collaborate, then it's very likely that we all collaborate at some point. So we know that this is known as simplicial closure, and is observed in some real-world networks. So and if you let time goes on, then it is conceivable that all cliques are filled up, and so that makes the clique model a reasonable model. The other reason I choose clique model is that it is something I can compute with. What the Betti numbers tell us? Betti numbers roughly tell us repeated connections. If you look at citation networks, you can very often, when you have a giant survey paper comes up, it will fill up a big hole, and that will decrease the Betti numbers. The idea being that it cones the hole in the network. So the holes kind of tell you something about the gap in our understanding, and the higher Betti numbers roughly corresponds to gaps in our higher understanding, which I can draw you a series of pictures to try to make sense of that, but I will not do it here. So Betti numbers tell us something about the graph. I do not have a full explanation of what like precisely they can tell us about. Okay, I should say what I can tell you depends on what you want to know. Okay, so this is a very preliminary exploratory work on like trying to combine topology with network science, and I do not claim that I have like a full picture of what this should go forward. But this is something simple that we can compute and something we can say about. And I think like when more people look at this, we may have better answer of like what it can tell us. Yes.
Yeah, so like you're just assuming everything closed out.
It's a simple model, so that I can compute things.
And what do we care about when